Good evening, everybody.
Good evening.
Okay.
How are you?
I'm good. I'm good. I'm good. Okay. Just give me a moment. I'll start sharing my screen.
Okay.
My screen is visible.
Pardon?
My screen is visible. It's sharing.
Yes, yes.
Oh, yes, perfect. Okay, just a moment. Before we begin, any just like queries from the previous lecture or in general before we begin?
Um, I just wanted to know, have you thought of what the final evaluation is going to look like?
So the final evaluation is uh probably going to be a written exam. Yeah, it's probably going to be a kind of written exam, which
Okay.
is going to be proctored of sorts, and we're still
Okay.
trying to figure it out on the back end. What type of exam is going to be like? How are we going to proctor it and everything? But highly likely, I think it's going to be a written exam.
It's going to be at home online?
It's going to be at home and online. Yes, precisely.
Okay. All right. Okay, thanks.
Yeah, welcome. And I know alarm bells start ringing in people's ears when they start hearing there's going to be an exam. But in my opinion, uh, uh, doing the assignments properly, uh, trying to do it by yourself or with aid or whatever should suffice into your understanding as how like into your general quantum field theory problem solving understanding that should like get you through the mountain when it comes to the
That
final
should be a
exam.
good enough preparation.
It should be a good enough preparation. Of course, it for those of you who are over reliant on ChatGPT, uh, it's not going to be good enough preparation. So yeah.
Are you going to give us some former, last past year's exam questions? That would help.
This is gonna be our first. This is gonna be our first exam of
Oh,
Physics
okay.
Without Frontiers. This is gonna be
All
our
right.
first exam, so unfortunately, no such path questions
We're guinea
exist.
pigs.
You guys are our guinea pigs. But yeah. Anyway, I think there's a question in the chat. Let's- Yeah. What are the internal symmetries? Those will be more fleshed out when you're going to do when they're gonna teach you quantum field theory. Those are gonna be well more fleshed out internal symmetries and what are external symmetries. The Poincare symmetry is external symmetry, okay? Because it's the symmetry of the coordinates which you're with, because when you're doing quantum mechanics, what is it? It's like uh okay, I'll use this. Like it, let's say for a generic function psi, okay? It doesn't necessarily have to be uh quantum field theory. It can also be a classical field theory. Even in classical field theories, fields are represented in terms of functions, right? Or kind of, yeah, in terms of functions, right? That function denotes whatever property of the field that it has. So it has to be dependent on some four vector x, right? Where I mean x is equals to x mu, which is basically x0, comma, x vector. Okay? So this is x capital, not capital, sorry. This x. You have some kind of function which gives you which gives you like the the certain understanding of the dynamics of this quote unquote field. Okay. So internally, you have it dependent on some coordinate. So, like external symmetry is this coordinate, this wave function, right? Or sorry, this function in general, or this field, right? This field being invariant under a Lorentz transformation, right? And that comes in line with the Poincare symmetry that we spoke about. So this has to be equals to like lambda mu nu x nu. Okay? And for that to hold true, there are a couple of stuff that you have to consider and everything, which you will of course learn later on. And the notion of internal symmetries are basically act on the field itself. Okay? It's not acting here. Okay? Like let's say for example phase change. I shouldn't get this. Psi of x when it goes to e to the power I alpha, uh, psi of x. This kind of like external, this kind of transformation is this is a U1 transformation, for example. This kind of transformation is what is known as an internal transformation. Okay, where even in this kind of a transformation, you will find that like the norm psi is still going to be the same as let's say if this is psi prime. Psi prime. So yeah, sound is not clear, I think. Is am I not clearly audible to the rest of you?
You're crystal clear.
I'm crystal clear. Okay, I'm hearing from other people. Sound is very low, actually. I don't know how I can't turn. Let me test the settings a little bit. Uh, Okay, I don't know. It's looking at like my microphone is at pretty good, pretty high enough volume. Anywho, it's still it's still okay, no problem. Okay, hopefully you can hear me enough. It's 1 minute. Okay. Oh, I forgot to mention before I actually started. This session is recording, so yeah, I should have said that before I started recording. But uh, to the person who asked, do you understand what is meant by internal and external symmetries in the case of quantum field theory? Well, what that means? Mihir Patel. It's still not clear what the internal and external symmetries are.
Echelon and order even functions.
No? Sorry? Okay, no one's responding, so I'll move on. Move on
I
to
have no
two.
problem. I have no problems.
Okay. If
I
no
can.
one's responding, okay. I'll move on to today's lecture of sorts. Today we're going to be delving not deep, as cursory as possible into quantum mechanics, right? No, this notion doesn't come from odd and even functions. If you're talking about phase change specifically, or it's not coming from odd and even functions, or like, but like, yeah, functions, like, yeah, it's not coming from there. You can conflate it to that, but it's not exactly that because external and internal symmetries is not a group theory term. It's more of how a certain kind of symmetry uh, manifests itself when you're trying to do quantum field theory. Quantum field theory requires two types of symmetries to hold true, and to understand the dynamics of quantum field theory, two types of symmetries must hold true. Of course, Poincare symmetry must hold true, and a lot of these internal symmetries, which are known as the gauge symmetries, these hold true if these gauge symmetries keep the action invariant. Okay, like let's say you have an action S is equals to d4x. The measure. I know you guys are you lot are used to writing the action like this dx, but that is only for like the action of something that is only dependent on one variable, right? So if you're going to have four different variables, which are all four different variables that are dynamical themselves, the measure, the integration measure has to be four-dimensional, right? So you have if for you have the Lagrangian, right? Inside the action goes the Lagrangian. You have the kinetic part and some kind of potential part, right? A kinetic part, potential part, or like it could also be like some could be. I mean, yeah, kinetic plus some mass term plus some potential. And would what is the necessity of internal symmetries is the fact that when these these things, which are functions of some kind of field, right? When some kind of transformation occurs to this field, and thus thus transforming S into some uh, S prime, the both S's need to be equal because action is not something that should change. Like the physics of the dynamics shouldn't given it shouldn't change because otherwise you're announcing unphysical you're announcing unphysicality, right? Nature does not work that way, and the way Lagrangian mechanics and Hamiltonian mechanics is devised, this has to hold true. Otherwise, what you're detailing is not a physical theory. That's what I mean. So yeah, that's how internal symmetries are acting on it. Okay. All right. So I'm sure like a lot of you are already privy to at least one course of quantum mechanics, if not a course. You lot are familiar with the general understanding of quantum mechanics. So this is going to be a very fast. Oh wait, is there anything special behind the units of Planck constant having off action? I don't understand. I'm unfortunately not understanding the question. Anywho, I'll progress further to today's, and then we can quell questions a little later. Okay. So quantum mechanics, for those of you who understand, it entails and details the dynamics of objects, or details of dynamics of objects that are microscopic in nature, right? Quantum mechanics, of course, remember this very importantly. QM is not a relativistic framework. Okay. It's not a relativistic framework. It's a non-relativistic framework where like your v the velocity of your particle is much less than the speed of light, this c, and it still has this sort of underlying like axiom of dynamics where you're dealing with point particle interactions. Point particle interactions, as you guys well know, they're zero-dimensional objects, right? And so
Uh-huh.
they're zero-dimensional objects that are interacting with each other or are interacting with the external, be it potential or no potential. So they are the simple extensions. The quantum mechanics is just an extension of classical mechanics into this kind of microscopic realm, and where classical mechanics kind of breaks down, right? Classical mechanics very famously has the Poisson brackets, where the position and the momentum, right, is supposed to give you like they commute, as in they give you zero, right? That's the definition of where this is the classical realm. This is the region where your simples where your classical equations take place, like Newton's equations of motions, Newton gravitational law, classical electromagnetism, and Einstein's gravity. All of these are represented by dynamics where you have your position and momentum when they commute are equal to zero. If you're unaware of what commutation this object looks like, it's just this. When you have x comma p, it's just xp minus px. Okay, and that's exactly what it means. So that's the classical realm. And when we move to the quantum realm, as we shall see a little later, it's not exactly equals to zero. Okay. Okay. Let's move on to a little bit of notations, because notations are very important moving forward to when you're going to do calculations, effective calculations. And so for quantum mechanics, the respective position and momentum parameters are a part of the vector space that is known as the Hilbert space. Right? What is a Hilbert space? A Hilbert space, simply put, is an infinite dimensional complex vector space. Right? And we denote the nature. Let's say you're defining a particle, right? The particle is defined by this quote unquote mathematical object called psi, for example, or for the time being, let's just call it alpha, where the dynamics of the particle is entailed by this kind of vector, which is called alpha. In using Dirac's famous Bra and Ket notation, very elegant notation, we utilize the notions of vectors because this is a linear theory. Quantum mechanics is a linear theory, right? Very famously, Einstein's equations are not linear theory, which is why you cannot organize them in such a neat manner as you can do with quantum mechanics. And also, what it means is in a linear theory, when you're solving a differential equation, the solutions are superpositions of each other. They simply add up, right? That makes solutions pretty easy to control in the case of linear theories, as unfortunately with nonlinear theories they're not, and require further enhancements and understanding. Anywho, so we denote the nature of, say, for example, a particle in motion with what is known as a state vector. Okay, the state vector is called a ket, which usually is always it's like written like this. This is the general notation of writing what is known as a ket. Now, some properties, a key property of ket is that a ket is additive. And where does this kind of these a lot of these properties are imbued from the fact that these are linear theories, like vectors are linear, right? You've done linear algebra, so you know vectors are built off of linear algebra, right? And a lot of, if I'm not mistaken, 7 different theories that make uh, a vector, but they're all related to linearity. So all of these things are uh, just trivial correspondences of linear algebra into quantum mechanics, but making them more physically feasible and physically more intuitive. Okay, so kets are additive, right? Which means if you have a ket alpha plus another ket beta, you're gonna get a completely different ket, which is called a gamma, right? You also have that when you multiply a constant c to alpha, it commutes basically. This kind of operation, it commutes with each other. It doesn't matter either like this is left multiplication, and this is, for example, right multiplication. It doesn't matter. They both are the same, given that C is a complex number. Okay, and a very important key uh, postulate, right? Quantum mechanics is built off of many important postulates, which without those postulates, and mathematicians work very hard to bring up these axioms of choice and postulates for quantum mechanics to be consistent. A very important postulate is the fact that, like, okay, a key physical postulate is that C, again, it's belongs to the complex number set. C of alpha is equals to merely alpha for C not equals to like 0. Okay. Of course, if C was trivially the identity, which is just 1 in the case of complex number multiplication, it's just trivially true, right? It's 1 times alpha would just give you, it's very easy to understand that it's going to be equals to alpha. But what if C is not equals to 1? And should it change? But a very important postulate is that, it shouldn't change. It should have no effect. This kind of uh, scalar multiplication of alpha of any kind of kets should not change your ket inherently. What that means is that, in other words, only the direction. Think of it from a vector point of view. The scalar multiplication is supposed to change the scalars, right? But in quantum mechanics, only the direction is important. Okay. Furthermore, we have what is known as an observable, because quantum mechanics is like, at the end of the day, quantum mechanics deals with a kind of function, right? You don't have a direct, like, classical mechanics, like interpretation of classical mechanics where they have no probabilistic nature. if a particle is here, it is for sure going to be, if you're doing something to it, you for sure know it's going to be, let's say, 2 kilometers away. You can say that with certainty because classical mechanics deals with dynamics that lead to a level of certainty, unless you, of course, involve chaos and everything, which this is a different kind of conversation. But classical mechanics is built on that kind of working ansatz that dynamics of any kind of object described by classical mechanics is going to be certain. Quantum mechanics is unfortunately or fortunately uncertain, and this kind of uncertainty you have to kick it into kind of functional distribution, right? That distribution gives you the understanding, okay, given where you are in the distribution, this is the probability of you finding the particle there, for example, or the particle having this kind of momentum, for example. So that kind of uncertainty is caked into a kind of distribution type function. Remember, they're distributions. Distributions inherently are different from functions, but they're called distributions. Okay, so in quantum mechanics, you then have to have a separate notion of what is known as an observable, or something acting on your ket. Let's say you have an operator that is acting, and it's built up of operator algebras, quantum mechanics. An operator acting on a ket will give you that observable. Okay, so let's define it. An observable is represented by an operator. They are, very importantly, left operating, okay? The kets. A hat of, let's say, alpha, your ket, gives you some observable A of alpha. So whenever I'm using a hat, this is a hatted, right? Whenever I'm using a hat, I mean an operator, and whenever something is non-hatted, it usually means that it's an observable. Okay. All right. So what we have been dealing with thus far is the ket space. The vector space that contains all of these ket vectors are called the ket space. Now, there exists a dual to this ket space. Right? And can anybody tell me what potentially is the dual of this ket space?
Bragg space.
Perfect. It's the Bragg space. The ket space has this like duality between what is known as the Bragg space. Okay. And so let's say, for example, you have an additive form of a ket space. How does that look in the dual version of the Bragg space? Let's take a look. C alpha, let's say, for example, of alpha. Of C beta of beta. These are they belong to complex numbers. Okay. They transform, they're dual to this following form: C alpha star entailing a complex conjugate. If C is equals to A plus BI, C star simply is equals to A minus BI, right? That is the complex conjugate. C alpha star of alpha plus C beta star of beta. Okay. And from all of these Brownian kets, we can start defining what is known as the inner product of quantum mechanics. Okay. So inner product, you can define it as this bra and the ket neatly organized in this form, where it's just basically your bra vector dotted with your ket vector. This is the inner product of quantum mechanics. Okay. And very generally, property of an inner product is this following property is equals to minus alpha beta. No, not minus, sorry. The complex conjugates of each other. This is very trivial to show. All you have to do is like exchange. Yeah, it's pretty trivial to show. Like you can show it in 2 seconds, in fact. And this relation is basically very easily it can be shown that if you have the same like if you have the same state, right? If it's both, if they're both, if both the Brownian kets define are states that are vectors that define the same state, and you take the inner product of the same state in inner product form, you basically it's trivial to show that they're not going to be complex numbers. They have to be real numbers, right? They have to be real numbers, and real numbers can range from minus infinity to infinity. Now therein lies a big problem. If you're going to have quantum mechanics have a probabilistic nature to it, right? Quantum mechanics has divides itself into state function or distribution function or distribution type functions, or say for example, if you're trying to talk in terms of bracket notation as states of vectors. If you're going to have a probabilistic interpretation of these functions where in the inner product, wherein you devise these distributions to give you a probabilistic interpretation once you take the inner product of it, probability has to be like positive definite, right? Probability there's no such thing as a negative probability. There's no such thing as a probability of you eating a cake as negative half, right? Probability is always defined to be from 0 to 1. That's how it's defined to be. Now, it needn't. Now that's how probability is defined to be. Now it needn't be when you normalize. Sorry, when you take the inner product of two state vectors, that you get something that is bounded between 0 and 1. It could run amok and wild and have values that are greater than 1, for which is why you utilize normalization tactics so that you stay in between that region of 1, right? However, you must artificially mandate that when you're dealing with physical state vectors that define dynamics, that define quantum mechanics, these state vectors, when you take an inner product of them, they have to be positive definite. So, a very important second postulate is that when you take the inner product of the same state, it must be greater than or equals to 0, which means that the inner product needs to be positive definite. From a physical point of view, as I mentioned before, but let me formalize it better here. From a physical point of view, It is the safeguard to the probabilistic nature of quantum mechanics. Okay. Okay, let me check the chat if there are a couple of questions. Are symmetry breaking processes are not action conserved? You asked a very beautiful question, which I will not answer. I will. You will see when you look at spontaneous symmetry breaking of SU2, and yeah, I'll leave that little uh, that notion of beauty to that lecture. So it's a fascinating concept. If for those of you who are unaware, spontaneous symmetry breaking is what gives uh, a scalar Higgs particle its mass. Okay, that's what was discovered by LHC, the Higgs particle. So yeah, and also it gives rise to the mass of W plus minus and Z vector bosons, because typically gauge bosons like photons, W plus minus, and like gluons, like typically, trivially, you look at them as like, if let's say you come from the worlds, if you come from the simple world of thinking of like gauge bosons as simply as photons, you think of them as like long range forces, which means they're massless. But to attach masses to these kinds of gauge bosons, it involves the utilization of these of the concept of spontaneous symmetry breaking. Okay. I gave a lot of Nancy Fancy terms here, but you learn more in detail. That takes at least one or two classes or lectures to really flesh out. So I'm not gonna try and detail anything here. You learn that. Anywho, moving on. There are no more questions. Another point to be noted is that let's say you take the inner product of two different vectors, alpha and beta. They're equal to zero, and irrespective of however you order the inner product of alpha and beta and alpha, and they're going to be equal to zero if and only if alpha and beta are orthogonal. Okay. Similarly, there's duality conditions to how operators act on kets and how operators simultaneously act on bras, right? Let's say you have an operator x hat, which is operating on your ket. The kind of duality allows you to write the operators to change like this, where x hat changes as x dagger, where x dagger is called the adjoint representation of x hat. What makes and in quantum mechanics, you require these operators to be Hermitian. And what makes them Hermitian is the fact that x hat is equals to x hat dagger. This is the Hermiticity condition. Okay. Very important thing to know. It'll come in handy when you have the product of two different operators, x hat, y hat, and you're daggering them. It simply means y hat dagger, x hat dagger. Okay. This is how it transforms to. And there's also the notion of outer products, which I'm not going to delve deep into. the notion of outer product, you have inner products that look like this. Outer products be basically made to make operators of sorts. So outer products look like this. The notion of outer products can be used to basically form like operators. Okay, next time. If inner product, if you can think of if let's say you're thinking in of these vectors in terms of like the linear algebra point of view, if you attribute the ket vector as some kind of column vector, right? You have like A, B, C, D, and let's say you attribute the bra vectors as some row vectors, right? They're dual to each other. A, B, C, D. So like when you do beta alpha, if I'm defining my betas and alphas, okay, 1 minute. Quantum mechanics doesn't have negative. Okay, I'll answer you in a second. Let me just flesh this out. So beta and alpha, the inner product is going to be what? A, B, C, D dot. I should not write this is A, B, C, D. I should E, F, G, H. E, F, G, H. You have A, B, C, D. What this is going to give you is just a real number, right? Which is what you expect from an inner product dot product, right? But when you do an operation like this, it's not going to give you a simple real number. It's going to give you a matrix because the operation is what is known as a tensor product. And if you want to know how tensor products are kind of evaluated, just Google how to evaluate tensor products and you'll find out how tensor products are evaluated, but you're going to get a matrix. Okay? 4x4 matrix. Because this is 4-dimensional. This is 4-dimensional. Okay. And these can be made into operators. Okay. Quantum mechanics doesn't have negative probability. Is it the manifestation of quantum mechanics or nature? Because we see negative probability in Dirac equation. Okay. Lot to uncover here. There is no such thing as negative probability. Probability by definition has to be positive definite, right? The probabilities always have to add up to 1. That's the definition of probability. And given that quantum mechanical nature is uncertain, you must then utilize tools from mathematics that deals with uncertainty, right? Certainty is having the probability of a job being done as 1. Being uncertain is having a job being done be in between 0 and 1. And since the dynamics, when it comes to microscopic dynamics, they are uncertain, you have to utilize probabilistic natures in the first place, right? So quantum mechanics, if it deals with uncertainty and you utilize the framework of probability, it has to have a probabilistic interpretation, then it has to be positive definite, right? And in terms of negative probability in Dirac equation, Dirac equation does not imbue in and of itself the understanding that it gives rise to negative probability. It gives rise to negative energy states, is I think what you're trying to mean, right? That's not the same as probability. They predict kind of negative energies, which you have to interpret properly. So those negative energies, Dirac had a problem with because he was like, this cannot happen. I'm giving rise to negative energy states. Energy is something that is always defined to be also positive semi-indefinite. Energies cannot be negative. If energies are negative, then it's unbounded. That's a big problem. Unbounded from below. That's a big problem for physical type theories. Now, the interpreted problem with that, assigning negative energies to those kinds of particles, which are described by the Dirac equation, is the fact that he was thinking of it. He and of course uh, him and a lot of other physicists at that time were thinking of it from a particle point of view. But it's the fact that these negative energy solutions are just, if you interpret it and like put more different type of intuition into it, like an ad hoc, another type of intuition into it, is the fact that these are not negative energy particles, but these are particles that are by nature antimatter. They're antiparticles of the particles that you know. So it's not that they carry negative energy, it's that these antiparticles have these type of energy associated to it. They're describing antiparticles of negative energy. And again, you learn more about it when you do like fermionic field theory or Dirac field theory. So yeah, I hope I was able to answer your question. And very importantly, if you're going to attribute a Dirac equation to quantum field theory, right? Let's say you quantize the Dirac equation and you get quantum field theory out of it. Quantum field theory does not have a probabilistic interpretation like quantum mechanics does. Okay, quantum field theory doesn't work that way. Now, in an ideal scenario, quantum field theory should give you like a probabilistic interpretation, but it doesn't. Because when you're doing any form of modern uh, phenomenologically relevant quantum field theory work, you're doing perturbation theory. You're doing perturbation theory of the potential, and that cannot give you inherently like at high energies for quantum field theory. That does not give rise to the probabilistic theory that quantum mechanics is. Quantum field theory is not built with so quantum mechanics is also not built with ansatz, right? Quantum mechanics came out of trying to understand the dynamics of like microscopic particles. It's only later on that mathematicians thought it imperative to imbue in it a lot of axioms that make it mathematically whole, right? And to make sure that the postulates have the dynamics of have quantum mechanics be mathematically consistent. No, mathematical consistency is not found properly. By mathematical consistency, I mean like pure mathematical consistency. Mathematical consistency is not found when trying to understand quantum field theory. Okay? Exactly. Scattering amplitudes isn't the same thing. It's not the same thing. It's not going to give you the direct it's not going to give you the direct probabilistic interpretation you will find in quantum mechanics. Scattering amplitudes are just unfortunately very, very different, right? There are other like ansatzes that you put into it, which work with quantum field theory and give you phenomenologically relevant answers, but they're not mathematically consistent. They're trying to figure out mathematical consistency, but it's proving to be very difficult. They've been at it for a long time, and it's proving to be very difficult. So yeah. However, quantum field theory is still a working theory, right? Quantum field theory works, gives you relevant answers, and uh, ironically, quantum field theory is also the best theory that has ever been. Like from quantum field theory, when you start doing Standard Model is thought to be as the best theory that is available to that is has been able to be devised by mankind across all sciences. I'm not just talking about physics, across all sciences. So even though quantum field theory is not a mathematically consistent framework, it gives rise to theories that have happened to be the most consistent theory in the history of humankind and human sciences. Okay. Anywho, moving on. So, uh, in classical mechanics, you have the definitions of momentums and positions very trivially. You have like T, which is just like classical mechanics is what? It's mv vector, right? And like it doesn't really matter. And X is just X, right? Pretty trivially understood. However, in quantum mechanics, these are operators that act on a state. That need to be acting on a state. So in quantum mechanics, the momentum operator, okay, is minus I h bar d by dx. I'm denoting here d by dx for single variable dynamics. And so if you were to extend it to CD, it'll just be minus I h bar, the grad vector, like whatever coordinate system you see pleased to it. Okay, so that's the momentum operator, and you have the position operator, which is just x hat. Okay, this is how you build and figure out your kind of uh, find out from your distribution function, which is your psi, which is a probability distribution function, what is the what is the momentum going to be, or what is the position going to be for a certain interval or whatever. And let's say we pretty well know the Hamiltonian, right? The Hamiltonian is described as p squared. Well, okay, let's first write it like this. It's kinetic energy plus the potential energy, right? Which very famously, the Hamiltonian is described by two variables, which are the momentum and position, right? So if you're going to describe the kinetic energy, you can describe it purely from the potential point of view. Sorry, the momentum point of view. You can write it as p squared by 2m, right? And the kinetic energy, the potential energy, just leave it bare for the time being. Like, let's say I'd call it just v of x. Okay, it can take the form of whatever you want later on, depending on your theory. So quantum mechanics has Hamiltonian be an operator, right? And because they have to be operators that are acting on state. So your H, let's say, for example, acting on a state, psi, should give you the total energy of the state as well. Okay? So Hamiltonian, we know it as p squared by 2m plus some v of x that's going to be acting on psi, right? And then you have energy here. Now the energy E of psi, right? Now the energy operator is the following. I h bar d by dt. Okay. So yeah, this function psi of x is also time dependent. And for the time being, this is single variable, right? This x is not a 4 vector, it's just a single variable x. So p squared, which is your momentum operator, which is minus I h bar ddx squared times 1 by twice m, plus, again, you have your v of x, and this act on your psi of x comma t. And you have, on the right-hand side, I h bar d psi of dt. Now this just becomes minus h bar square d square psi by dx squared. There's a 2m here, plus v of x that acts on your psi, x of t, psi is a function of x of t. And then here you have I h bar d psi of dt. Right? This is your famous Schrodinger equation. Right? Okay. Now, this is of course, a differential equation. This differential equation, given on the kind of potential, you put your particle with a probability distribution of psi. You solve for that potential, this differential equation, and voila, you find you find what your state equation of your probability distribution for the particle should be. Okay, it involves very tricky solutions for differential equations. So, but we're not going to go deep into that for this lecture. You can see a very trivial example from any book that you can find out for different types of potential, like particle in a box. This is a very classical kind of problem, and also particle that is just being undeterred by any kind of potential. So you can also solve for that. Again, pretty trivial solution. Anywho, moving on, let me give you the canonical commutation relationships, right? And quantum mechanics, these are very important. Or you have, let's say, for example, now, yeah, let's say, for example, you have x hat I, x hat j, they're going to give you 0. In the same way, if you're going to commute potentials, they're also going to give you 0. Okay? These operators are orthogonal to each other. xi hat and xj hat, they're orthogonal to each other, which is why they're giving you a 0. Now, in the case of trying to commute, remember I told you previously in quantum mechanics, when you're trying to commute the position and the momentum, you're going to get 0. In quantum mechanics, that changes. When you try and commute x hat I, let's say, for example, and p hat j, you're going to get I h bar delta ij. Again, delta denotes the Kronecker delta, which, if you're unaware, is 0 if I is not equals to j, and it's 1 if I is equals to j. Okay, and this is this 0 in general, right? And yeah, for classical, if you have x and p, it just gives you delta ij. Okay, which is just 1 if, for example, you have I is equal to j. Some other important identities that you need to be privy with, and they're going to come in handy when you're going to do because you're going to learn canonical quantization first in quantum field theory. So these are identities that you should have in the back of your head, because derivations involving canonical quantization are long, and you need to have all the tricks up your sleeve. Even saving computation of one line is saving 2 minutes of extra work and at least 5 to 7 minutes of extra thinking. Okay, so keep this in the back of your head. There are some relations. Let's say you have the same object commuting with each other, they'll give you 0, right? And then you have this a comma b. It's very simply is equals to minus b comma a. These are all independent of quantum mechanics. These are just relations of some of these are just relations of just pure commutation algebra of commutators. And then you have, if you have like an observable A, let's say, or an operator A that acts on a number C, it'll give you 0, where C is a number. Okay. You have this A plus B, comma C. They break down linearly. You'll just get, it's the same as A comma C plus B comma C. Okay. This particularly comes pretty handy. And then you have finally what is known as the Jacobi identity, which is A comma B comma C plus it follows a cyclical property B comma C comma A plus C comma A comma B is equals to 0. These are some important important identities you should keep in the back of your head. Anywho, now dynamics without any kind of time evolution is of no use to physicists, right? You need to have your state then, if you're defining the mechanics of your particle, say, for example, with a state, you need to realize or understand more mathematically how the state should evolve with time, right? So the time evolution of state is simply written as you have alpha T naught, and it's dependent on T. It comes from doing a unitary transformation. Remember from yesterday, a unitary transformation that acts on alpha, which is just dependent on T naught. Okay? What's happening is this unitary transformation, U T of T naught, when acted on like your alpha, which is defined for T naught, gives you the time evolved state kit after some time, T. Okay? It's a unitary evolution as well, right? What do I mean by unitary evolution? Unitary evolutions come from operators that look like this. U dagger, U is equals to 1. This is
Preserving.
it. Huh?
Non-preserving. Probability preserving.
Probability preserving. Yes, exactly. So these are unitary operators or unitarity. At the end of the day, what will happen is these end up preserving, yes, the probability because of how you devise the inner product of quantum mechanical wave functions. Okay. Very importantly, right? I mentioned before, when you're taking an inner product of two types of kets, say for example, they're of course, if you're defining something physical, they're going to give you a positive definite number. But more often than not, it's not going to give you a number that is trivially less than 1 or around 1. It's going to give you a number that is much greater. So it's up to you, the physicists, to normalize your normalize your wave function first, and then start calculating for whatever observable you want to calculate out of the wave function. So a normalized wave function will give you this, right? At T naught, which is your at initial time. After normalization, it should give 1. Right? What is this physically? What is physically happening here? You're asking, what is the probability distribution of my particle, for which nothing is occurring, to exist? It should all add up to 1, right? That's the probabilistic interpretation, right? For nothing happening, and if you're integrating it for over all of time and everything, it's just going to give you like all of space for which is going to give you 1, because if for that defined space, that particle must exist. You integrate over that space, so it's going to give you 1. Now, the what would happen if you have time evolution, right? If you were successful in normalizing, when you utilize unitary operators to time evolve your operators, to your ket or your bra operators, you will find that even for time evolved kind of, even when time evolution takes place, alpha T naught t. This is time evolved form. When you try and get the norm of them, it will still give you 1. Okay? And uh, this is really the main reason you use unitary operators when you're trying to do quantum mechanics, right? And the evolved version will remain as such. And of course, you have to make sure it's normalized beforehand to know this. Okay, so unitary operators also are imbued with specific composition law. Okay, there exists a composition law which states that if, let's say, for example, the unitary evolution takes you from T naught to T2, you can have the following, step by step. You can have it be like this. This is unique to quantum mechanics and makes calculations pretty easier. Okay, so this is all I wanted to talk about in general for quantum mechanics, and I just want to give you like a quick rundown for the simple harmonic oscillator, as since the simple harmonic oscillator is at the essence of the type of potential that we deal with when we're doing quantum mechanics, right? It's the simple harmonic oscillator type dynamics, because the simple harmonic oscillator, and one can ask why always a simple harmonic oscillator, because let's say you have a potential, you have v of x, right? And like a generic kind of potential v of x, a potential well source v of x, okay? So if you try to Taylor expand of v of x around, let's say, x, or Maclaurin expand around x naught, you can expand it like this, right? Some kind of function. Let's keep it up till the third derivative. Okay. Now, very simply, this you can set to 0, right? It's a constant value. It's not dependent. V of x naught is just going to give you a real number. You can set this to 0, right? So this, very trivially, you can set this to 0. What happens here? At maximal solutions or minimal solutions, this goes to 0 as well, right? This goes to 0 as well and doesn't really have much of a contribution of sorts. What about, so usefully, you're left with really higher order terms, okay? And of course, the higher you go, the less relevant they are. Higher orders are lesser and lesser relevant or you assume it as such, that they're lesser and lesser relevant to the dynamics of your potential, the higher derivatives that you go in, okay? So we are left for the time being. Let me pose for you guys that for the time being, these two are the most important parts of our potential if you approximate it. Why the second term is 0? Second term is 0 when you're in maximal solutions, right? Or minimal solutions or stationary points. That's when it's 0. I'm just giving rise to why a lot of potentials can be approximated to harmonic oscillator potentials. So this looks like takes the form of your typical harmonic oscillator. Right? What does the harmonic oscillator potential look like? It's v of x is equals to of m omega squared x squared, where these are just parameters, right? And if you're going to link it to this, m omega squared is just v double prime, right? And so if you take the double integral, it's just going to give you the potential energy for a harmonic oscillator, right? Anywho, can somebody tell me, let's say I told you for with absolute, let's say this is an abstract like uh wide, but the third term is not harmonic oscillator. It's an anharmonic oscillator. You mean the fourth term? You meant the fourth term, not the third term, right? Rana Ahmed? Okay. Third. But it looks like a harmonic oscillator. Why would you say it's an anharmonic oscillator? It's an x squared term. The square of the position is trivially always associated to a harmonic oscillator, right? Harmonic oscillators have this. This is the potential energy for a harmonic oscillator. Some prefactor times x squared. Okay. Anywho, let's sorry, yeah, the fourth term. Yes, you're precisely correct. So the fourth term is an anharmonic term. But for the time being, assume I'm a crackpot physicist. I don't know much about anything, and I'm asking you guys that okay, for the time being, I am going to forget anything higher than third orders, right? I'm gonna forget fourth, fifth, and nine infinite orders. Like convince me to convince me why a physicist generally does not think of an harmonicity and only trivially considers harmonicity when you're trying to approximate a general potential. Remember, I'm still not talking about harmonic oscillators. I'm asking you why, for a generic potential, we always go to a harmonic oscillator, right? I've already given you the general answer as to why to neglect these two terms in trying to approximate a general potential. But why not this? I'm assuming, okay, the four derivatives are too much. Like we can drop this, but why not this? Why can't I have my generic potential because there's a minimum in the square term? Perfect. Exactly. If you do not have, if you have an x to the power 3, your potential is unbounded from below. What would your function look like if it's a square or if it's a square potential? Looks like this or like this or whatever, right? If it's a cubic type potential, it's going to like come from below some way, right? You see, you cannot stop it from being negative. You have to actually physically put cutoffs into your theory. You have to physically put cutoffs. Okay, our potential, even if it's x cubed, it's only defined for above x is equals to or greater than equals to 0, or x is just greater than equal to 0. Now, those are physical constraints that you have to ad hoc add later on. But so yeah, so the argument is the cubic term with x attached to your position, they are unbounded from below, and we assume v triple prime is much less than v double prime to have any kind of discernible effect to the dynamics of the theory in the first place. So harmonic the simple the keyword here simple harmonic oscillator is good enough. So that should give you kind of motivation as to why try and approximate every single potential to a harmonic oscillator, and why physicists always use a simple harmonic oscillator. And as somebody else posted, Abdul Hafiz, simple harmonic oscillators are indeed easy to solve. Okay, so we're going to be dealing with the simple harmonic oscillator. Let's review a little bit about what the simple harmonic oscillator says in quantum mechanics, right? So you have the Hamiltonian, as always, as p squared by 2m. And if you have the potential stated to be the harmonic oscillator, you have m omega squared x squared by 2, right? Where, of course, omega has this following relation, k over m. Okay. Now, uh, immediately trying to solve this utilizing brute force this differential equation, when you like this is your Schrodinger equation looks like this, right? And when you start putting half m omega square x square psi of xt, which is equals to I h bar d psi by dt, blah blah blah, trying to solve this differential equation just by using brutalistic techniques of solving differential equations, it's pretty difficult. It's very difficult to get your solution of psi. But Dirac, the brainiac that he was, found a way to circumvent around trying to solve the differential equation in the first place. He just invented two new variables that are neat properties themselves. Okay, so it is convenient to reframe the operators. Remember, these are p hat squared, x hat squared in quantum mechanics, of course. Operators x hat and p hat, they are Hermitian, of course, to non-Hermitian operators known as a hat and a hat dagger. Okay? Now, you define these a hats and a hat daggers as the following: square root m omega by 2h bar, x hat plus I p hat by m omega. A hat dagger is merely the complex conjugate of a hat, as you well know from what daggering effectively means. M omega by 2h bar, x hat minus I p hat m omega, right? And what happens when you try and find a combination relationship between a hat, and a hat dagger? A hat, comma, a hat dagger is, you will find that if you put these in, simply bake down to 2h bar, it's pretty easy to solve. You can try it by yourself. Minus I, x hat, comma, p hat, plus I, p hat, comma, x hat, right? This gives you my what was it? It was IH bar, right? Yes, gives you IH bar. And this, since this is the opposite, it will give you minus IH bar. And if you solve it, it ends up just giving you 1. That's how A hats and A hat daggers were defined. So that you get, when you're trying to commute A hat and A hat daggers, you get a 1. Furthermore, we define this operator called N, which is known as the number operator. You denote it as A dagger A. Okay, so how do these operators come to use? Take, for example, if you multiply the two operators A dagger A, what do you get? You get m omega by 2h bar. The two squares multiply basically, and you have x hat square plus p hat square by m square omega square plus I by 2h bar, a commutation between x hat and p hat because of all the minus signs involved. Okay, you can reframe this entire thing because, as you can see, you have the x hat square term and the p hat square term. You can reframe this as the following. This entire thing evidently then represents the h hat, the Hamiltonian. The Hamiltonian divided by h bar omega minus half. You see, A dagger A is equals to this. What you can then do is rearrange this equation and you can find H hat purely in terms of operators and numbers. A dagger A plus half, right? And we already defined what A dagger A looks like. It's N. So, oh, there's a H bar omega. So H hat merely is N plus half H bar omega. Okay? And N, it's an operator, right? It's an operator. When applied to, let's say, state vector N, gives you this number N of N, where this N needs to be, for consistency, a non-negative integer number. Okay, I'm not going to prove it, but take it as it is, right? And if, say, for example, you applied the H hat operator on this state N, what happens? It's basically applying A dagger A plus half H bar omega, which is just N plus half. Let's just do it like this. A dagger A plus half H bar omega, which is being applied to the state N. That's right. You get merely N plus half H bar omega. This is the eigenvalue, right? This is the eigenvalue, basically. And this eigenvalue is attributed to the energy, because when you reframe quantum mechanics into like eigenvalue type problems, it's what happens is H hat, when you apply to a state psi, it gives you the eigenvalue, which is energy. It's just the real number, right? Energy. So then what we find is that from this type of, when we apply H hat to your state N, you find that your En takes this following form, N plus half H bar omega, as in your energy now comes in like discrete forms, right? N is a non-negative integer value, and N can range from 0 to, effectively, there's no top ceiling, right? So like at E0, you just have half H bar omega. At E1, it's going to give you C by 2 H bar omega, and so on and so forth. So you get solutions for your energy as levels, right? You're discretizing the energy distribution, and you're getting levels of energies where the solutions effectively would have stabilities on, right? Yeah. Anywho, moving on to a couple of reasons why we devise N A daggers and A's in such a manner. Let's say you try and calculate the commutation relationship between N and A. Right? N and A, you try and solve it. N is what? A dagger, A. I'm not I'm not gonna give any inherent hats for the time being. So understand that these are all operators, and that, okay, you know what? I'll just give hats. A hat dagger applied on A, and then you have A here. And so this can be split up, right? You have A dagger hat. Here you have A hat commuting with A hat, which is always going to be 0, right? And then you have A dagger hat commuting with A, which is equals to 1. Which is equals to 1. Sorry, minus 1, because A commuting with A dagger is defined, it gives you 1. So the opposite is just going to give you minus 1. And so what you're left with is minus A, right? So when you try and commute the operator N with a hat, it gives you minus a, right? Minus a hat. What have and very easily it can be shown that when you're trying to commute the n hat operator with a hat, it gives you a dagger. Okay. All right. Now, how is this useful? You will find that as a result, when you apply, let's say, n a dagger on a state n, right? You can split this up. This breaks up. You can split this up as the following. You can write this as n a dagger. Let me write it this way. N a dagger, I can write it as n a dagger minus a n dagger plus a n dagger, right? I can always rearrange it. This part would cancel, and it would leave me with this n a dagger. But I do this for a reason. Okay, this is the same as that. And by doing this, what I can be left with is this is a commutation form, right? This can be rewritten as n comma a dagger plus there are all these hats that are missing. Plus some a hat n hat dagger, which is then being applied on your state vector, your ket vector, right? So a hat, this we know is very trivially just a dagger, right? So what are you left with? You have a dagger here plus a hat, n hat, dagger applying on n, right? So this is very simply just going to give you this dagger here. Large dagger. Right. It ends up just giving you n minus 1. Sorry, n plus 1 a dagger n. So, and here, of course, on the left-hand side, you had n hat a dagger applied to n is this. So, as you can see, like applying these, it just gives you this for the time being, except this. And in the same way, if you have n hat, a hat applied on a state vector, you're going to get n minus 1 a of n. Okay. Now, this kind of means that both of these types of equations mean that if you have, let's say, a general a hat applying on n, and you have another pure state vector n minus 1, are the same up to a multiplicative constant. As in, a hat applying to n is the same as some multiplicative constant c that you get from applying to n minus 1, right? And what does that mean? If you're trying to then normalize it, n, and applying a hat dagger a on n, this is going to give you what? C squared, right? Which means the c can be written as square root of n. Therefore, if you write it all in terms of n, you will find that the physical realization of applying these a hats on some state n returns you square root n and it changes the state vector to n minus 1. Similarly, the operation of a hat dagger applying on n, if you attribute a hat dagger applying on n and purely a state vector being n plus 1, and there's only a constant n that is the n plus 1, and then you can do again the kind of normalization, put it under the inner product, and then you'll find that a dagger n applying to n and then requiring that your state vector changes as n plus 1 returns you square root of n plus 1. As we can see, the physical realization of applying these operators, a hat, for example, let's just talk about a hat. A hat, when applied to an operator n, merely reduces it by one step. You get returned a state vector that gets reduced by 1. So the application of a hat kind of, if you're thinking about it like from a Mario point of view, Mario is in between of some step or something, and like applying an a hat to the traversity of Mario's going to go down one step, right? And the application of a dagger is just Mario going up one step. So this is how you can manipulate in harmonic oscillator type potentials, like these. Either you go up an energy level, for example, or you go down an energy levels, which is why these operators are called ladder operators. A hat and a hat daggers are called ladder operators. A hat is known as the annihilation operator. You're annihilating one level and going down one level. A hat dagger, for example, is the creation operator. You're going up one level. And these are in general the basic tools that we utilize when we're doing analysis with simple harmonic type potentials, which are then going to be useful for when you're doing quantum field theory, because quantum field theory is just the framework of infinitely many harmonic potentials at your disposal. And that's how quantum field theory, the framework of it, is it devised in that manner. So yeah, this is all I wanted to discuss for today's preschool lecture. These latter are time dependent, right? What will happen if these operators are time dependent? Yes, these operators will also be time dependent. Yes, of course. Depending on the kind of picture that you're working with, these operators will also be time dependent. Okay. Any more questions? I'll turn off the recording if you guys want. Then you can ask the questions as much as you please.